So, some basic definitions, reminders about notation with set theory here. Set theory is pretty straightforward. It's the relationship between set theory and basic logic is really transparent, which you'll see here. So I think we can do this pretty quickly, and I think the most efficient way to do it is really just to go through my prepared notes. I tend not to do this, but I think it's important that we work through the process together, but I think we can just cruise through this uh, pretty quickly. So we'll keep that same example that we were using in the past lesson of a sample space of the outcomes of two coin flips. Just going over some symbols here, this little symbol here that looks sort of like a simplified version of a euro sign. It is supposed to be sort of a stylized E. It's telling us that something is an element of S. Okay, so HH, two heads, that is indeed an element of S. And as we can do with most mathematical symbols, we can draw a slash through it to mean it's not an element of. So three coin flips is not outcome in the sample space of the two coin flips, right? You can't get three heads if you're just flipping the coins twice. In terms of sets being equal to each other, they're equal if they have the same elements. Okay, so this would be equal to, if I write them in a different order, T, 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 H, 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 T. This is maybe a good place to point out something else about sets. You might be thinking sets look kind of like vectors, it's kind of a list of things. With vectors, remember, vectors and matrices, the positions of the elements matter. So if you have the same basic numbers in a vector, but they're in a different order, they're different vectors. Not true with sets, okay? So sets, the order doesn't matter. Another difference between sets and matrices, which are also like, collections of things, in a set, the element is either in it or it's not. There's no such thing as being in a set twice, okay? So if we by mistake wrote something like, or we're going through some kind of derivation that we ended up with something like TT in here twice, that's it's redundant. That is just equal to TH, HH, HT, okay? So being in the set is being in the set. There's no such thing as being in it more than once or anything like that. Okay, and we have subsets and supersets. So we can use this this symbol, which you kind of think of as a C for contained. HHTH is contained in S. Set is contained in another set. If every element in the first set is an element in the second set, and we can write it the other way if we want as well. We have a set with no elements in it, and it's denoted with this 0 with a slash through it. That sort of, and it sort of works like a 0 in set theory. It's a useful thing for us to have when we're going through derivations with sets. And then the other basic operators for sets are the equivalent of the basic operations in logic. Okay, so we have set union, which is a set of things that are either in A or in B. Okay, and that is indeed the key word there. So set union is the equivalent of or in logic. So if it's either in one or the other, it's in the union. I'm skipping over the extended union for a minute to say something about intersection. We have intersection. If an element's in the intersection of A and B, it means it's in both of them. So the set intersection is the equivalent of a logical and. They have to be in both things. And both of these union and intersection, you can write long unions, take the union of A1, A2, A3, A4, the things that are in either A1 or A2, A3, A4, however many. And when we're thinking about those unions of an arbitrary number of sets, this notation can be helpful. Okay, so it looks like summation notation. We've got the big union here instead of the big sum. Down here, we're saying what the starting number is, what the ending value is. It's an efficient way to write this kind of idea. Same deal for intersection here. And the final logical operation is not negation. And for that, we have the set complement. So that is written with the set with a little c for complement in the subscript. A complement is the set of everything that's not in A. So again, the equivalent of a not in logic. And these two little points down here, I wouldn't exactly say that they're the definition of the complement of A, but they're so close that they're hard to separate from the definition of a complement. They come in very handy in long logical processes. One is just to note that the union of A complement and A is the sample space, right? You start with A, how do you get to the sample space? Oh, you take its union with all the things that are not in A. The other little point worth noting here is that the intersection of A complement and A is always the empty set, right? Because how do you get a complement? It's the things that are not in A. Like I said, pretty straightforward definitions. We'll have one more set theory lesson that will take you through a few rules and properties. So I'll see you in there.